Hello?
Hello.
Yeah, can you hear me clearly?
Yes.
Can you skip the introduction? I have to run to another conference about 15-20 minutes walk away after this.
Okay. Sure. So
Yeah,
yeah, in
I'd like to
35,
rush through
40
this.
minutes, 35, 40 minutes you can run.
Okay, okay, I'll try.
So it's a great pleasure to have Vivek Borkar in this symposium for Mrinal Ghosh. So Vivek is actually talking about in search of treasure, which is Markov solutions.
Okay, thank you. It's a pleasure to be sort of virtually participating in this meeting. And I'm known to talk too fast. I think today it will be a virtue for a change. This is the outline. I'll just give a brief sort of background on diffusion process. Probably most of you know anyway. So I'll sort of quickly go through it, then describe what's the Markov selection problem, which arises due to non-uniqueness of solutions, and there's a classical approach due to Krylov, and it has some limitations that also I'll highlight, and then a new approach based on viscosity solutions, which I've been at for a while with my collaborators, which I'll soon give the details and further issues finally. So just to set notation, this is the old notation. So the transition kernel of a Markov chain, and denote by small p a comma t given x comma s, which satisfies the Chapman-Kolmogorov equation. In case it's time homogeneous, you replace t and s by this single t minus s. Okay. The diffusion process or Markov process with continuous paths, and in fact, it's a result due to Denkin, which says that your failure process with a continuous path whose generator has all compactly supported smooth functions, then it has to be actually it has to the generator has to be second order elliptic operator. So it kind of continuity plus some technical conditions characterize at least the class of diffusion. And the classical, I mean, the oldest approach has been to think of it as some kind of in on a short time span of delta. It's kind of like Gaussian, except that the mean and variance covariance depend on the current state. Hello? I'm hearing some music. Anyway, let me continue. So the conditional mean is x of t plus delta, conditional mean of x plus t plus at t plus delta minus xt given the current state, some function m of xt. Similarly, for the conditional covariance matrix, you have some symmetric non-negative definite matrix, and you can define a square root of it. I mean, not uniquely, but nevertheless, you can define a square root sigma. So I'll always write this covariance, conditional covariance, incremental conditional covariance as sigma xt, sigma transpose xt. So these are called respectively the drift. M is called the drift, and sigma is called the diffusion coefficient. And I'll say that it's non-degenerate if the least eigenvalue of sigma transpose is bounded away from 0. I'll also assume throughout, I don't mention it only once here, that I'll assume the linear growth condition on the coefficient, so that on M and sigma transpose, that in particular means that I don't have to worry about the solutions blowing up in finite time. So they're when they exist, they're defined for all time. Okay, so the most oldest approach is Kolmogorov's forward and backward equation. And so you look at this second order operator, we call script L sub x. And suppose the transition probability has a density, then Kolmogorov derived these two equations. One is the backward equation, which is in the initial time. The time variable is the initial time. And this is also initial state. Basically, you fix the conditions at a terminal time and look at the process from 0 to on the closed interval 0 to capital T, say, with conditions prescribed at capital T. And the forward equation goes the other way, of course, the right way. I mean, starts from 0 and goes forward, except that it's more complicated. This L star is the formal adjoint of L, and now the variables are different, of course. The T is the forward time and Y is the forward space variable. And this is nice, but it needs classical solutions using PD theory. and in particular it involves non-degeneracy and or hyperellipticity or something. So it's highly restrictive framework. So the next big development was the semi-group approach, where these people, probably others, use exploited Helios-Theta theory to come up with the semi-group formulation. So define this transition semi-group. So just from Chapman-Kolmogorov equation, you know that is a semi-group. Again, if it's time homogeneous, it's a one parameter semi-group, and let's T be its infinitesimal generator, and D script D of T is domain. And then if I mean a priori it maps bounded measurable to bounded measurable, but if it also maps bounded continuous to bounded continuous, called a failure process, and strong failure if it maps bounded measurable to bounded continuous. And okay, I'll skip the definition of a stopping time. So this I guess all of you know. And the failure process is a strong Markov for free. This is, of course, this is something true in discrete time. In discrete time, all Markov are strong Markov, but not discrete Markov chains, but not necessarily true in continuous time. But the failure process do have that property. So you have these semi-group counterparts of Kolmogorov equation. But again, this is quite general, but not enough. So, for example, if you have diffusions with say Lipschitz continuous sigma, but only measurable, bounded measurable M, say, you should be able to make sense of it. It's particularly it's extremely important for control people, but there you get into trouble. You cannot explicitly characterize DT, so that has limitations, and that led to the another development which I will come to soon. But before that, this kind of concurrent development or parallel development by I mean, it's attributed to Ito, but then there was the one-dimensional case was already done by Dublin using a different technique, and that was uncovered in 2001 or something. So he also deserves to share the credit. So this is the stochastic differential equation defined in terms of this Ito integral, and you can write diffusion in this form. But the main thing I want, okay, so there is this notion of strong solution. If you can construct the solution on a given probability space and with a given Brownian motion, etc., and a weak solution if the probability space is not prescribed, and you look for a solution on some probability space, and the uniqueness is in terms of law. So in strong case, the uniqueness is almost sure uniqueness. Two solutions have to match with probability 1, and they have to be versions of each other. They have to match at each t. And weak solution means that their laws have to match. So they could be defined on entirely different probability spaces. Now this is the main thing. So the final kind of crowning glory of this business was the martingale problem formulation of Truk and Varadan. So they defined a martingale problem for say given initial distribution mu and this operator script L as following. So it is that the process X solves the martingale problem if this object is the martingale with respect to the natural sigma field, and it's a unique solution to the martingale problem if it's unique in the solution is unique in law, where L is now called I mean you specify L and the generator. It's not unlike I mean it's called the extended generator now, and its domain is something you specify. So you have a lot more freedom here. So here I have taken f of C2b of RD bounded continuous, twice continuously differentiable functions with which are bounded continuous along with the first and second partials bounded. So it's very convenient to work with, and in fact this theory has been pushed to great heights, and you can find, for example, Ethier and Kutz for an excellent treatment of that. So the problem is that if, for example, if sigma is non-degenerate Lipschitz, or if both M and sigma are Lipschitz, this is well posed. But if M and sigma are only continuous, you have only existence but no uniqueness. Though you can characterize all solutions, all possible solutions can be characterized. This you can find in chapter 12 of Struck and Verden. But the following is true. So the existence actually comes from Euler-like approximation, not a big deal. And the martingale formulation, you can write it in terms of sort of expected value of something being 0, of not a single expected value, but sort of infinite family of expectations being 0. And therefore, convexity and compactness of these conditions hold under weak convergence, and so the solutions solution set can be shown to be convex and compact. So it's denoted by script Ax for a given initial condition X or initial law nu. The convex, compact, non-empty set of solutions to the martingale problem. Okay, then the Markov selection problem is given script Ax. You have to find you have to select actually P star X in Ax for each X so that they patch up to satisfy Chapman-Kolmogorov, so that you have a legitimate Markov process. A priori, it's not free. I mean, it's not obvious that you just have for each initial condition you have a collection of laws on the space of continuous functions. You can pick one for each condition, and they will automatically solve Chapman-Kolmogorov. In fact, I mean, the Stoke-Verdon characterization of all solutions shows explicitly that there are non-Markov solutions. So the classical very clever trick is due to Krylov. And so what you do is take suppose it takes a rational countable dense set in 0 infinity, open interval 0 infinity, and an fi of bounded continuous functions which are form a countable separating class. That means if two measures mu and mu prime give the same integral on all fi, then mu must be equal to mu prime. So fi can separate the measures. And then you define the Gij gamma. Gamma is the law of the process. So I will define a functional of the law Gij gamma as this object e to the minus RIT ft dt. So it's like the resolvent. This is two indices, but I can just string it out and call it Fi, so lexicographically or something. And then I start with this A0x, which is the original solution set, and inductively define AM x for m greater than or equal to 1, by AM plus 1 being the set of minimizers over AM of FM gamma. Okay, so I have this collection of countably many functionals. So I start with the solution set, minimize on it F0, and because of continuity compactness argument, the set of minimizers again will be, you can show that it's compact, convex, non-empty. Then on A1, they call that A1. So on that, minimize F2 and so on. Keep doing that, and you get a nested family of decreasing family of compact, convex, non-empty subsets. And the intersection you can show is actually singleton, and you will come to that. Before that, this is the fact which is used. I want to highlight that because this is stochastic control conference. So for a stopping time tau with respect to the natural sigma fields, if the law of x is in am of x, the law of x tau plus dot is in am x tau. Okay, on the set tau finite. And the punchline is that this follows by a dynamic programming argument, which is not surprising because Krylov sort of came out. I mean, his background is originally from stochastic control. I mean, now he does hardcore PDU, but he's well groomed in this, and that helped. So it's a pure dynamic programming argument which ensures this. And that also, okay, so by finite intersection property, you get this, and then you can, by our choice of the separating class, etc., you can show that it's a singleton. That's not a very hard thing, but the punchline, as I said, is the dynamic programming argument, which shows that what you get out of it is a strong Markov process. And this is interesting because the proof does not show that it's failure; it just directly shows a strong Markov. Whereas the classical way of thinking is that you first show failure property and then claim strong Markov. What's the problem? The problem is that it's not unique. It can depend on what FIs and RIs you choose and in what order you minimize. Okay. So one would hope for some natural kind of family which you pick. So is there a principled alternative possible? And that's what I'm going for. So it's based on philosophy also attributed to Kolmogorov. So this is in this famous survey paper on chaos and strange attractors by Ekman and Roel long back 80s, I think, in Reviews of Modern Physics. And it doesn't give any reference. That's why I'm mentioning this. So Kolmogorov suggested that you, in case of ill-posed problems with too many solutions, you pick a physical solution by adding some non-degenerate noise to regularize it. So, for example, as in stochastic differential equation, very often you add noise and it actually improves things, because I mean, the simplest way to think of it is you have some random variable x with very bad distribution. You add independent y, which is Gaussian, say, and distribution of x plus y will be smooth. So that's the same logic which works here more or less in a fancy form. So you regularize things by adding noise and then let noise tend to zero to get a limit solution. Okay. There are several success stories. There's the stochastically stable equilibria and evolutionary games. Evolutionary games, you kind of cook up some learning dynamics. See, as it is, the Nash equilibria are often far too many. So you cook up some incremental learning dynamics to model the bounded rationality of the economic agents, and then look for its equilibria, if any. And if you are lucky and they do converge, then you call those equilibria as your sort of favored Nash equilibria. But even those are too many. So you add noise and let the noise go to zero, and that typically narrows the selection significantly, sometimes to a singleton. So those are called stochastically stable equilibria. Then viscosity solutions themselves, I believe, originate with this methodology, because you add new times Laplacian to the differential operator. You basically you get non-degeneracy, and the new is a sort of like the viscosity coefficient in fluid mechanics. Then there's some work by Shankar Shastri in Berkeley doing his PhD thesis to recover things like hysteresis in nonlinear electric circuits as limits of regularized kind of dynamics with noise. Okay, so this is based on these two articles. So both look at the same problem basically, but when this work with Suresh, we took from the off-the-shelf results from on viscosity solutions from User's Guide by Crandall, he and Lyons, and because neither of us is a viscosity expert. Suresh, of course, knows much more than me, but we took off-the-shelf results and plugged them in. So that put some limitations. So conditions are rather strong. And this has been extended thanks to this postdoc, Anup Sumith Reddy, who is actually in math department. He is very knowledgeable and expert in viscosity solutions. We were able to generalize these results significantly. Okay, so you take bounded continuous M and sigma and can look at the backward equation. And the classical solutions may not exist, but viscosity, if it's degenerate, then the viscosity solution does under suitable conditions. And of course, I mean, if conditions are good enough, it's unique. So that's what I'm going to leverage. So let me quickly go to the definitions for sake of completeness. So you say an upper semi-continuous function U is a viscosity subsolution of that equation if these two inequalities hold at a global maximum x prime t. Sorry, this first inequality holds at global maximum of x prime t prime of u minus phi, where phi is some smooth function, and the terminal condition also holds with an inequality. And this is kind of easy to motivate. I mean, if you were twice continuously differentiable, then at the local at the global maximum, their gradients would match, and variance Hessian would solve that inequality, because at the local maximum the Hessian has to be non-negative definite. So you plug it in, you get an inequality. So you plug that in the just kind of this is just a heuristic. I mean, don't believe what I'm saying, but it justifies this kind of inequality. I mean, it tells you that you should expect this, let's say, and then this Jones et al. Have proved that that's enough. Super solution is a symmetric definition just by reversing inequalities, so I won't get into that. And it's a continuous solution is a viscosity solution if it's both sub and super solutions. And the uniqueness is usually hard to prove, and that needs something called comparison principle. So I'll get to that later. So the plan is going to be to take some non-degenerate so take some epsilon perturbation by adding small noise. This is one possibility, but it doesn't have to be this. But it has to be non-degenerate, and then you have a unique classical solution, which are viscosity solutions as well. And then let epsilon go to zero and look for the viscosity solution in the limit. And under the conditions we use, it's unique, and therefore you have a unique viscosity solution for the backward equation. So suppose I define this U superstar, U substar. These are some steps that go into this whole business. And then, so starting with some continuous U, so starting with some U, I cook up this U star and U substar, U substar and U substar, and these are super and sub solutions with this inequality. And the comparison principle essentially allows you to show that they are equal. And so this is the comparison principle. So it sort of bounds sup of mod U minus V by the value at the terminal condition means 0. Okay. And that implies uniqueness of the viscosity relation. So in fact, for this work, these are the hardest parts. I will come to that later. I'm just giving a sketch of the whole argument. So we take this script L epsilon, the extended generator for the U corresponding to U epsilon. So this is the backward, non-degenerate backward equation. And this is the unique classical solution, which also has this nice probabilistic interpretation of being conditional expectation. Then you let epsilon go to 0, and it will converge to the unique viscosity solution, as I said. And the X epsilon process corresponding to L epsilon with a fixed initial law. I mean, it's tight, that's easy to show using standard moment bounds. And let X be one of its subsequential limits, and then we have to worry about what X is. Okay. So what I've done with Suresh is that there exists a Feller solution with the same one-dimensional marginals as X. And in fact, all subsequential limits have the same one-dimensional marginal, and you can pick one solution that is Feller. So this follows from the fact that you have a unique viscosity limit for the backward equation. And what one does is take backward equations on intervals Si, comma Ti, Ti bigger than Si, for Si and Ti belonging to some countable dense set of time points, and the F belonging to a countable separating class. So you have a whole countable family of backward equations, and you go through this viscosity limit one at a time by using a diagonal argument. And finally, you'll end up with this. So you get a Feller process. And of course, you have to, the Chapman-Kolmogorov simply follows through the limiting argument because U epsilon satisfies it. So in the epsilon going to limit, 0 limit, it is also satisfied by the limiting U. So you get a U associated with, I mean, you get a whole family of U associated with these intervals S comma T belonging to some, say, rationals, and F belonging to some separating class, and then some argument using the usual representation theorem tells you that this will have the form you desire, namely the conditional expectation with respect to probability measure. So that's roughly the sketch. Okay, this I already said, the Chapman-Kolmogorov equations just pop out of the limiting. And because U is continuous, the limiting thing is a limiting process you get out of this also Feller. And what Sumith managed to do is that it's in fact a unique limit in law. So there was one simple fact Suresh and I had not observed, noticed, is that we proved sort of we focused on pairwise marginals. We were always thinking of Markov kernels, but you can actually, with all the continuity, etc., freely available, you can show convergence of all finite dimensional marginals. So and then with some extra effort, you can show that it is in fact a unique limit and a unique Feller process, which you extract out of the non-unique sets by this process. So this uniform convergence of U epsilon to U on combat plays an important role here. And the major contribution, which I have to say that I should have probably put my name at least in smaller font, if not invisible. This was what Sumith managed. We could not use off-the-shelf existence and uniqueness results, but using all kinds of recent results from literature, including a PhD thesis, he managed to prove the bulk of the hardest part in the paper is the comparison principle, and he managed to push it through. And we impose some Hölder continuity conditions, which I think have not been given because they are ugly. I'm saying they are ugly, but they are vastly more general than what the previous paper had. So that's the kind of saving grace. It should be okay. I guess I have that on the next thing. Future directions. it should be possible to. I mean, my kind of dream is that this should be a very general scheme without any unreasonable restrictions. So I'll leave that to future generations of viscosity solutions. Much of maybe Sumith himself will pursue it. I don't know. Then another important thing, this is even a further kind of distant thing, is extension to control diffusion. So I want to mention one thing that there's a parallel problem in control division. So you would like to have a control that is a Markov control, in the sense that the control depends only on the current state and the resulting process is Markov. So these two are different conditions. If I have in a degenerate case, if my control depends only on the present state, that does not automatically imply that the process is Markov. It's just like non-Markov solutions to the degenerate diffusion. So you want both the control and the process to be Markov. And in some conference, Vardhan suggested using Krylov selection for the process for this proving this, and promptly two people from the audience proved that independently. One was Ulrich Hausmann, who I think did it for the exit time problem, and the El Karui, Nguyen, and Jamang, they did it for the finite horizon problem. So, but again, can one kind of see this? Can one? So they use Krylov selection, of course, but can one do this for control diffusions, where we'll need to drop basically continuity, which is already, I don't think the viscosity solution, and I believe there are some limited results without continuity, but I don't think it has reached any level of maturity as far as I know. And then also every probabilist should like a completely probabilistic proof, so that you can afford to not know too much PDE, and that's that even further goal. So I want to thank you and my best wishes for Mrinal for a healthy and active retirement. I want to leave you with this cartoon, which does not reflect what Mrinal will be like, but nevertheless it's funny. Okay, so very quick questions. It's actually 7:30 for me. I have to grab a breakfast and then dash off to the University of Porto from wherever I am. But I think I can take some questions for 5 minutes or so.
So if you have any quick questions, please ask. Manju, please.
Hello, is anybody there at all? Is my question.
Hello? Is it on? Yeah. Borkar, this is the mic, right? No, it's not on. Yeah, it is there, but I don't think it is. I'm audible. Can you hear?
Yeah, I can hear.
Oh, okay. Sorry. No, I had a very simple question. So maybe it's related to this probabilistic thing you said. Is there a natural way to discretize this in time and or space? He hasn't heard. Okay. Okay, it's fine. I can.
I can't hear you at all.
Maybe I ask again. Can you hear me now? No, I think he's. Oh, but BB could hear.
Yeah, I could hear.
Yeah. So, Vivek, can you hear or not? No, it's okay. Leave it. Gopal.
To this point. Hello. We can't hear. Actually, Borkar can't hear it, so we go to the next talk. I think so. We have to leave him a chat, probably saying I think probably you can't hear us. Shall we leave him a chat? Chat.
Even though Borkar can't hear, let us thank him.
Yeah, let us thank him. Yeah. Hello, Anup. Can you hear?
Yeah, I can hear. How about you? Can you hear me?
Yes, I can hear you. Yeah.
Okay.
That's good. So we have very nice international communications. So it was nice, a good time for Borkar actually, and we had a very nice talk. We wanted to interact with him, but we missed his lines again. So now we have another speaker, Anup Biswas. I mean, you all know him from ISER Pune. He has been doing excellent work so far that we know. So he's giving a talk here in this symposia, existence uniqueness results for nonlinear integral differential equations. So you have about 35 minutes and 5 minutes for the interactions. Yeah, thank you, Anup. Please carry on.
Okay, thank you for this nice, excellent introduction. I have prepared a short talk because it's just before lunch, so I don't want to make people wait. Okay, so this is a project. It was planned with. I'm hearing some echo. Is it clear enough? Can you hear me clearly?
Yes.
Okay. So this project was actually originally planned with one of my longtime collaborator, Adi Arapostathis, but many of us know that he passed away last year. So I pursued this project with Saibal, my postdoc, and so I'm going to talk about more about what this is project about and what are the main results and difficulties, rather than going into the finer details about motivations and its connections with many other things. So the project is about finding a solutions to a differential equations that looks like in this complicated form. So we have infimum over some index set, this mathcal t, and we have this operator here where delta is defined like this, and k is a kernel, but as you see that I have divided k by y to the power d plus 2s, which is the fractional non-local kernel of order s. And then I have a drift parameter, and then I have another function g, which is known as the running cost, and then some lambda. So the goal is to find u and lambda that satisfy this equation. So the problem from the PD point of view, this is simple, that I have an equation and I want to find the solutions. Why this PD? I'll come to that much later. But now, if I replace this part, which I have with a delta, k tau, and y, so this integration, if I replace it with some Laplacian operator, then this becomes a traditional control problem, ergodic control problem that you can find in that red book by Arapostathis, Borkar, and Ghosh. Now that I have changed the operator to something else. Now, just because I have changed the operator to something else from local to non-local, it creates a lot of difficulty because the same approach does not really gives you solution to this problem, because there are several level of hurdles that we encounter, and that's what I want to discuss in this. Okay, now the assumptions that I'm going to put, that this guy k here is uniformly continuous in y and tau. Note that I do not pose any assumptions about compactness of this mathcal t. This is any index set. Okay, I'm not going to impose any such condition on this. and I want my K to be symmetric in Y. That's something you see for fractional Laplacian. So, and it is the symmetry that gives this delta in this form, because in general in Levy operator you get a different form, which is the first order approximations ux plus y minus ux minus gradient of u times y. But then if your kernel is symmetric in y variable, you can do a simple change of variable and make it in a nicer form. And I want my S to be bigger than half and 1 because I have a drift involved here. So this S being bigger than half will help me in certain regularity estimate. Now, why this problem? So coming back to control, probably this is the only slide where I'll use the stochastic interpretation for this particular PD. So if you stick to a compact metric space and let U be, denote the collection of all stationary Markov controls. So these are all Bodel measurable functions from RD to T. And then you define the controlled extended operator, so extended generator. So you take any control V and then you define one extended generator. Here the IV corresponds to the non-local integrations, and then BVX dot Vx is the drift, control drift. And suppose this the martingale problem is well posed. If this happens, we can define one minimization problem. So the minimization problem is I want to look at the ergodic cost corresponding to the running cost function G. So I look at the long-term ergodic cost. I want to minimize the ergodic cost and call this value lambda star. And then it is sort of known that, but though the exact calculations or rigorous calculation has to be done, but it is known that this lambda star would be the lambda star that we have seen in our PD in the slide before. So the HJB problem corresponding to this particular problem is actually nothing but the problem I was showing before. Okay. So this is the motivation for studying that particular problem. Then once we have the HJB problem or unique solutions to that ergodic HJB problem, one can talk about detailed connections like whether this lambda star is actually the lambda star that we can solve, we can get from the HJB equations, and what about the minimizing control, the characterization, etc. that can be done. Okay. Now to solve this problem, the strategy is again pretty much standard. One can try to follow whatever is done classically by Apostasis, Borkar, and Ghosh. So what you can do, you can start by looking at the discounted problem. So what is the discounted problem? You look at the problem, you add an extra parameter here. So this alpha Wn, which was not there in my original problem, this is called the discounted factor. So here are the notations I'm using. Is my L tau is basically this non-local plus the drift. So I put it together. And then I take a discounted factor, and then G tau originally was there. So I look at the discounted problem in bounded domain, and I solve the problem in the bounded domain. Okay, and this was already done in a work of Chen Mo in 2017. Okay, so now that is a step 1. In step 2, I'm talking about the broad strategy for solving this kind of problem. In step 2, what we do, we extend the domain to the whole Euclidean space. So now that I have solved the problem in bounded domain, I have to extend it to the whole Euclidean space. Now, the classical way to do this, we have to prove this family Wn is equicontinuous with respect to n. So I have some amount of stability. And then using this equicontinuity, can we pass the limit in the viscosity sense? Now the viscosity. Can you come again? I couldn't hear if there was a question. Was there a question? I can't hear anything actually.
Hello, can you hear?
Yeah, I can hear you, but was there any question?
We haven't heard also. I mean, we have heard just like yours.
Okay, okay. So I'll continue.
Yeah, thank you.
So the main problem here is, first of all, if we have equicontinuity, you can pass the limit in the viscosity sense, the same viscosity notion that Vivek was defining in his talk, but now it is for the non-local version. So I don't want to get into the definition, etc. for that. There is a viscosity notion, which is a very weak notion, and we can use that if my Wn is equicontinuous. So the requirement on Wn is very minimal. It doesn't really require any stability on the differentiability property or anything. Equicontinuity is good enough. But only trouble is now my L, or in particular I, is a non-local integration. So I have to pass the limit inside the integration. So equicontinuity is also not good enough. I need some information about the growth of Wn. As my n tends to infinity, my Wn should not grow very fast so that this integration becomes infinite. So this is where also I need to be extra careful, which the local problem did not address. So this is where the problem is, passing the limit inside the non-local integration. So I have to be careful here. Okay, so this is the first hurdle. Now, so once we have solved the problem, the step B was done. Step C is what we have to do, we have to take the normalization. The normalization is I just subtract the point W alpha 0. This is called the normalized function, and observe that the normalized function solves an equation that looks like this. Okay. And if these normalized functions are also equicontinuous, then I can again try to pass the limit in the viscosity sense. And if I can pass the limit in the viscosity sense, what would happen is that this term alpha W alpha bar, so this will go to 0 because W alphas are bounded because they are equicontinuous. So that will go to 0. Alpha W alpha will go to some value lambda, and I'll have a solution for my original ergodic HGB equations, which I started with. Okay, so that's what what I said. I have written it here, that if this family is equicontinuous, I can pass the limit in the above equation to get a solution of the PD or integral differential PD I started with. Okay, so that's the again the same problem would occur, that I need a growth bound on this W alpha bar to make sure I can pass the limit inside the non-local integration. Okay, next challenge is, now I have a solution, so I have to prove this solution is unique. This is where even it becomes more complicated, because the traditional method that I know from this book by Vivek Borkar and Ghosh is that they use a stochastic representations. And given the generality of our model, I cannot use stochastic representations because the martingale problem is known to be well posed for a particular class of drift. And what we wanted to do, we wanted to avoid that path and to prove uniqueness for this particular model that does not use stochastic representation technique. So that becomes another challenge for us. And so what now I'm going to explain is that under what conditions these challenges can be overcome. Okay. So first thing to remember, that somehow I need to control the growth of my discounted problem so that I can pass the limit inside the integrations. And one standard assumptions in this setup is known as stability conditions, because the stability conditions, the Lyapunov function gives a barrier functions or a support for the growth of the value function. So this is what actually we have taken. So suppose we take a function v, which is known as the Lyapunov function, and h that satisfy this Lyapunov condition. So this is known as the Lyapunov condition. So something of the same sort was also there in a Suresh talk. He showed something that was geometrically stable, but it is just a stability condition. And I want my g to be in the little o of h, which means that my h grows faster than g. So this two condition gives me control of the solutions that I get at different levels, so that I can use some sort of dominated convergence theorem to pass the limit inside the integration. Okay, and this is a bit scary, but you can avoid it. The A3 you can avoid. So what we are doing here is that we can let our B and G to have to be unbounded. They need not be bounded, but this is a little more general than being bounded. So for simplicity of the talk, you can stick to B and G bounded. But otherwise, if you want it to be unbounded, so then these are the conditions. The first condition is the one that can help. And then this is the Helder continuity of B, G, and K. So this is required for some regularity estimate, which I'll come to it later. So these are set of conditions, but you can forget it because these are not very important. Now, so as I said, the step 1, solving the discounted problem in the bounded domain, was already done by Chinch and Mo. Now we want to go to unbounded domain. So to go to unbounded domain, the main trouble was the non-local integrations and equicontinuity. So what we can do, we can apply maximum principle and can show that my WNs are bounded by K divided by alpha plus V, where V is the Lyapunov function. And this is for all n. So therefore, I have a global bound on Wn for all n. Okay, so this can help me to prove, use dominated convergence to pass the limit inside the integration. And then I can use the Helder estimate done by Schwab and Silvestre recently. So if I combine this two, so this Wn will be equicontinuous family, and I can pass the limit inside this equation in the viscosity sense. So everything now is done, done in the viscosity sense. These solutions are not yet classical solutions. Okay. Okay, and I get a limit of this equation. Okay, but then I get a solution in the whole domain, in the whole Euclidean space RT, and W alpha is bounded by this factor K by alpha plus V. So if I multiply W alpha by alpha, so there becomes locally bounded independent of alpha. So that's one of the observations I need, because I have to pass limit at alpha W alpha at some point 0, the point with respect to which I'll be doing the normalization. Okay. This is another important thing one need to observe, is that with a little more care, one can also show that this W alpha will be little O of V. That means the V will grow faster than W alpha. Okay, so that needs a little more calculations, nothing else. Now step C. So what we do now, we again normalize and look into these equations, as I said before. Now the problem here is, again, I have to find a bound for this W alpha bar, but the previous calculation does not help, because these calculations does not give me a bound for this guy W alpha x minus W alpha 0, because there is an alpha factor sitting in the denominator here. So this calculation does not help me to give a bound. Now the classical approach, is what I said, that this bound is no longer useful, and the other approach to use Harnack estimate, so which was done in this red book and also very recently by Arapostasis, Caffarelli, Peng, and Zheng, for a different model, non-local model, but they also used Harnack inequality to get a bound on this W alpha bar. Okay, and this is this Harnack estimate is not available for this kind of operator in this generality. If you consider a general operator, the one we have here, we do not have Harnack inequality, so we are sort of one gets stuck if one takes this kind of approach. Now what we do is the following. So if we look into the maximum principle again, and then we observe that the W alpha bar x is actually less than equal to W alpha bar at a domain B, which is a compact ball, plus Vx. So the point is, so this again, one has to use the fact that each W alpha is in little o of V. So the point is, if we know that this guy is bounded, then my W alpha gets a global barrier function that it cannot grow faster than V, which is good enough for us to pass the limit inside the non-local integration. So the main main critical point here to prove that in any compact ball, W alpha bar cannot grow to infinity. Okay, And that's what we do, that we actually show that this quantity is finite and it uses a Liouville type property. We assume that this is not finite and we want us to do some calculations and to arrive at an equation that has a Liouville property and get a contradiction. Okay. And then once we have proved it, again, we can use a result by Sylvester and Schwab to prove that my W alpha bars are locally held or continuous, and again pass the limit in the viscosity sense. So this gives me the existence of solutions, and this is what step C was. Now the problem becomes, we can also show that my U is in the little o of V. So V grows faster than U. Fine. Now we come to uniqueness. Now the problem, as I said before, that there is a classical approach of stochastic representations where we get a representations for. So what we do in stochastic representation is, so the solution U that we have obtained here, we get a stochastic representations for the solutions. Okay, and then one proves that using the stochastic representation that any other solution must lie below these particular solutions that we obtain using this limiting process. But because we're dealing with viscosity solutions, we did not have that privilege to apply stochastic representations, number one. And second thing is, the martingale problem is not well posed for the kind of class you are looking for. At least not known. I mean, it's known to be well posed for a restricted class of drift and kernel. So now, how to prove uniqueness for this kind of problem? So one thing to observe is that suppose we have a classical solutions, that means I can define this equation classically. Suppose if we could do that. So this is the place where we need Helder continuity of the coefficients. Okay. Suppose we could do that, then what we could do is that we can subtract U and V and get, suppose I have two classical solutions, U and V, and then I can just subtract them and get to an equations like this. Okay. Once we have an equations like that, one can apply again Liouville property for this kind of problems. So because I know my U and V, okay, because I'm looking for uniqueness in this class, so one can use the Lyapunov function as super solutions and prove that any sub solutions to these equations, either you will have a lambda equal to rho and W has to be 0. So that can be proved using your Lyapunov function V. The problem is I have to couple them because they are viscosity solutions, and coupling the viscosity solutions with state dependent kernel is not true. And that is where I need to improve the regularity to classical solutions. And this is the next step is, so let's look into the classical solutions, that when can I say the solution is classical. So it needs a regularity known as C2S plus regularity. So it has to have a regularity a little better than C2S. Okay. So there is a result by Sarah in 2015, which says that if this term, whatever I have written in red here, is C alpha, then the solution here could be C2S plus. If the red, whatever I have written in red is in C alpha. So I can assume, but we have already assumed that my G tau is locally Helder continuous, B tau is locally Helder continuous. So what I need is gradient to be locally Helder continuous. So then the whole term becomes locally Helder continuous or C alpha. So to be the gradient to be C alpha, I need my U to be in C1 gamma. So at least if I can prove that my solutions are in C1 gamma, then my solution will be in C2S plus by a result of Sarah. Okay, and this is where the last thing is, what we prove is that you will start a more general equations which looks like this. Okay, and then what we could prove that if you have a viscosity solution, then they are locally C1 gamma. Okay, and then C1 gamma norm is bounded by the L infinity norm in RD because we are looking at non-local problems. So the value of U in the whole domain would matter, and the value of G in L infinity B1. Okay. Okay. And one more thing that I would also like to say here is this C2S plus regularity also depends on the global Helder norm of U. So how the Hilder norm of U behaves on Rn, Rt, that matters in this C2S plus regularity, and that part I have hidden here. It needs a little more calculations to prove C2S plus regularity apart from this C1 gamma regularity. So once you have C1 gamma regularity and then some bound on the Hilder norm of U in Rn, then you can prove C2S plus regularity here. And once you have the C2S plus regularity, the solution becomes classical. We can go back to this coupling argument with the super solutions technique here to prove that they are unique. Okay, so now the beauty of this approach is that this approach can be extended also for operator that looks like this, that you can have a more general integral differential operator. That means that has an elliptic part, a non-local part, a drift, and a running cost. Okay, so if you take an operator of this form, and here you do not need a kernel that satisfies a fractional order. It can be any Levy kernel. Okay, and the same idea works, and we get same existence uniqueness result. Now, two major questions that are still that remain unresolved at this moment is, we do not know how to address the same problem under the condition of near monotonicity. So for instance, if we do not assume any existence of Lyapunov function, but we want to treat the problem under the condition of near monotonicity, that let's say, for example, my running cost grows at infinity, grows to infinity at infinity. So it is coercive in nature. Can we solve this problem? At least existence or even uniqueness, I do not know, because we need some kind of barrier functions, and which is not very clear at this moment. How to construct the barrier function for a general G without imposing any Lyapunov condition. Okay. Now another one is the linear quadratic settings, which is very classical problem, but with a fractional operator. So this is the problem currently we are working on with Soibal, and we have existence result as of now. Uniqueness is the most difficult one, because regularity is a very difficult issue when your gradient has superlinear growth, and we are struggling with that. Hopefully we'll have something soon. Thank you.
So, is any questions for Anup, please? Can you hear Anup?
Yeah, I can hear, but not a question.
Okay. Anybody? Any questions? So, anybody in the of online audience? Yeah, Anup, just I have one quick question. I mean, go back to one slide, please. One, and yes, this one.
Mm-hmm.
Here, the B tau L and G tau L you are defining. What are these double index meaning?
No, this is for the game problem. We are getting the regularity estimate. So this tau, any index that you can take, as soon as they are bounded, B tau and iota, whatever, so they are bounded with respect to this index sets.
Okay, so basically these index sets are with respect to some games type of thing, right?
Yeah, so if anyone wants to apply the same result for game, they can do it. So the funny thing is, we could, in this particular paper, we have proved the uniqueness only for the minimizing problem. So that one might ask, why not for the game problem? One could have started with the game problem and tried to establish the uniqueness result for the game problem. So the challenges here is, so we can get existence for the game problem. The same thing will go through, but the uniqueness becomes a problem, because to establish a classical solutions, the operator has to be either convex or concave. So to keep the operator convex or concave, either you take supremum or infimum, but you cannot take both. And that is the main reason that we could not consider the case where it's a game problem. The game problem would not give me a classical solution, so the coupling would not be possible, and therefore I cannot talk about unique solution.
Okay. Okay. So I have another one, another question. Your things reminded me the general in financial market nowadays with jumps.
Yes.
Right? I mean, so basically that's the integral differential operator in general.
Yes.
So actually you can actually model now with some kind of control or some kind of strategic behavior. Control is really strategic behavior of some of the traders they can do. So modeling that in the financial integral differential equation form. So now you can solve get a existence of unique existence and uniqueness of those operators. I mean, looks like.
Yes, so the PD part is completely done now. So the only gap here is, see, the at least for I think if you have the elliptic part, non-degenerate elliptic part, I think well-posedness is more general. But if you do not have the elliptic part, but you are dealing with only the non-local one, okay, so then the well-posedness of the martingale problem, is known under a very restrictive circumstance. Okay, only the result I know it either considered B in Kato class, or K does not depend on X, or even if it depends on X, it has to be Helder continuous, which we cannot expect if it is a Markov control. So if it is a Markov control, I cannot impose that it has to be Helder continuous. So those restrictions are there. So I did not really get into those kind of problems in this project, but definitely it will be. We should try to connect this PD to the actual control problem and address that existence of minimizing control and how to characterize them. The problem is the martingale problem, that how to connect the stochastic differential equations to this PD in a vast class of stationary Markov control.
Okay. Any other questions? Yeah. You want this? You won't be able to hear.
You won't be able to hear. So I just wanted to add that the whole industry actually where they study the application of jump processes actually for financial models, and they actually connect the input PTs and stuff like that. There is this book by Ramakont, which was fully.
The voice is breaking. I could make it out that Imran is speaking, but I couldn't really
Okay.
What are you saying? But yeah, I mean, with the
okay.
Elliptic part, maybe well-posedness is there, but just if you look at the fractional part, I think only chain is
no,
that.
My comment was not specific to actually this PD or fractional or integral PD rather. It was about the applications of jump process or financial modeling, and there is a whole industry out there, starting with the book by Ramakont.
Yeah, I know that. Yeah.
So there, I think, especially this kernel K, actually, if it represents some alpha stability sort of thing, that means if it could be sort of thought of as the Levy measure of underlying sort of Levy process, then I think a lot of things actually will go through. So it's just that, yeah.
Yeah. Okay.
So with that, with real solutions for financial model strategies are near there. So with that, let's thank Anup.
Thank you.
We begin at 2:10 after lunch. Yes. Thank you. Yeah, thank you, Anup.
Thank you.
We miss everyone online for lunch, but we go. We miss everyone online for lunch.